Hey y'all, it's Miss Summers with your notes today on ocean currents. So our essential question, if we backtrack here, how does energy move through ocean currents? All right, we're going to look at how currents are formed, how they move energy around, and why that's important. Okay, so before we start on actually talking about currents, I just want to backtrack a little and review density with y'all because that's going to be important for one of these currents and how density of water is affected by two different factors. The first one is temperature. So we know when water heats up, when it's warm, the water molecules want to spread apart from one another because they're moving faster, and that makes it less dense because they're taking up more space. When the water is cold, the water molecules kind of get together, they bunch up because they're not moving as much, and that makes them more dense. And you can see this. We're not going to listen to this guy because he's kind of boring, not going to lie. No, I do not want to play it on the TV, but thank you. All right, so you can see how density of water is affected by temperature. So he's got cold water over here dyed blue, warm water over here dyed red. Okay, so wow, fancy. So as he separates that separation wow, that sounded dumb. As he allows this water to mix together, the cold water wants to stay down here on the bottom because it's more dense. Remember, things that are more dense want to sink. Things that are less dense, the warm water wants to rise. Cool. Okay, so we're going to exit all that. We're going to go here. We're going to go back, okay? The other factor that affects density is salinity, how much salt is in the water. So salinity means how salty. So remember, density is mass over volume, okay? If there is less salt, there's less stuff or mass in the water. So a lower salinity is less dense. A higher salinity, if I take a glass of water and I add a whole lot of salt to it, I made the glass have more mass because there's more stuff in it. Higher salinity is more salty. So we can see this as well. This is a really good video. So they have 0% salt here, that's low density. 3.5% salt over here, that's high density. This is about how salty the ocean is. All right, and you can see the very dense salty water wanted to stay down here at the bottom, while the less dense fresh water wanted to stay on top. All right, and it kind of sloshes back and forth, and you can see it's mixing a little at the boundary because you can see it's green. Now what's cool is they'll let it settle out. So you can see this is fresh water, this is like in between water, and this is salt water. They take this, they mix this completely up, so now they're making it one density here. Guess where the green one goes? Boop, 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 boop. It layers based on density. So the lower density is always going to be on the top. Middle density is here. The highest density is here. So very salty, in between salty water, and then fresh water. Okay? So we'll come back to that particular topic of density a little later in these notes. All right, so let's talk about what an ocean current is. It's a mass of water that flows from one place to another. All right? And ocean currents can be on the surface, so they can move horizontally, or they can be deep, where they go from the surface down towards the bottom. Ocean currents move water and more. So one of the ways people study ocean currents is by looking at things that the currents carry. So this story of these adorable little rubber duckies. All right, in 1992, a boat left China with a bunch of cargo containers, and one of the cargo containers contained 29,000 rubber ducks. All right, it got caught in a typhoon and a hurricane. The box that had all the ducks in it fell overboard and it broke open, and all these little rubber duckies ended up floating in the ocean. But they didn't stay next to the ship, they got caught in currents. So a lot of them kind of just drifted southwards towards Australia. But what was interesting is some of them drifted all the way across the Pacific Ocean. They ended up all the way over here in South America. But the coolest part is these that got caught in this northward flowing current, all right, went all the way up here between Asia and North America, around the North Pole, down here, got zipped up in the Gulf Stream, and ended up way over here on the beaches of Great Britain. So these ducks, it took them 15 years to get there, but still, ocean currents can move things from one side of the world to the other side of the world. So they're all connected, and that's why we care about them. All right, let's look at the, whoops, nope, go back. Let's look at surface currents. So surface currents are the ones that move horizontally. They stay at the top of the ocean. They stay at the surface. All right. These are currents that are caused by wind. All right. Wind creates these. It's pushing water a certain way. When we talk about climate and how climate changes naturally, we're going to talk about something called El Nino. El Nino. That's how you have to say it. And El Ninos affect a surface current, and it's because a wind pattern is affected, and it causes a whole chain reaction. Okay? So, many surface currents put together create what are called gyres. This word is pronounced gyre. It is a whirl or circle of water in an ocean basin. Okay, so I want you to look at this picture for a second, and hopefully you see a couple of patterns. There's two patterns I want you to see. Okay? Two patterns. Here's a gyre, there's a gyre, there's a gyre, there's a gyre. Do I expect you to know like the names of these currents that make up these gyres? Absolutely not. I really don't. Okay? But I do want you to know the patterns. All right? Let's start with the way the gyres are going. Okay, this line right here is the equator, right about there. Right about there, maybe a little lower. But you might notice all the gyres north of the equator, they spin to the right or clockwise. You're like, oh, that's really cool. And all the ones south of the equator, they spin to the left or counterclockwise. All right, that's not a coincidence. That's because of something called the Coriolis effect. Okay, so remember, the Earth is a sphere. The Earth is a ball, okay, and we're rotating, okay, we're spinning. Go back to astronomy, we're spinning, that's what makes night and day. That deflects which way water moves, okay? So warm water from the equator wants to go up north or south away from the equator, all right? Because of the way the Earth is spinning, it deflects it either to the right or the left. Imagine being on a merry-go-round, like an old school, like one on the playground that like you have to push and like you try to knock your friends off of because that's just how we are. All right. If you're sitting on one side of that merry-go-round and you have a friend sitting directly across from you, if you throw a ball, the ball's not tied to the merry-go-round anymore. All right. You're through it in a straight line. But because your target is moving, because the person you're throwing to is moving, it looks like the ball's not going to continue in that straight line. It looks like it gets curved to the right or the left, depending on which way you're spinning. That's the Coriolis effect. All right. The other pattern I hope that you see, the most important one, put a big old star. If you've already written these down, put a big old star here. If you haven't written these down, when you do, put a big old star, highlight this, circle it. If this is the only thing you write down, I mean, that's better than nothing. Surface currents maintain the balance of heat energy. Okay, so remember, this is the answer. This is essentially the answer to our essential question between the equator and the polar regions. Okay, the red arrows represent warm currents. This is moving warm water, and the wow, what's that color? It's blue. It's blue. Wow, that's a nice color. The blue currents are moving cold water. In the northern hemisphere, warm water moves from the equator towards the North Pole, okay, away from the equator. Same in the southern hemisphere. Instead of going north, though, it goes south towards Antarctica. All right, so warm water moves away from the equator. Cold water moves towards the equator. So this one's going up to the equator. This one's going down to the equator. This one's going down to the equator. This one's going up towards the equator. All right. Yeah. Why that's important? Why do I care though? It's because those currents affect climate. Those currents affect temperatures in places, and you're going to see that with your classwork today. It really has a huge effect on climate and temperature. So it's either going to warm a place up or cool a place down. So an example, the Gulf Stream is literally the only current I expect you to memorize. I don't care if you know the East Australian current that Marlin and Dory wrote. I don't care. That's cool if you do know that though. But the Gulf Stream starts here around the Gulf of Mexico, hence the name, and it rotates to the right, up towards away from the equator, and this warm water goes next to the British Isles and even up here towards Scandinavia. All right, if you look at this key down here, black are alpine areas. Alpine is it's like a coniferous forest where there's like lots of evergreen trees. It's cold, but it's not permanently frozen. Like summer is warm enough where the ground thaws out. Okay, like people obviously live here. This is where the Vikings are from. But if you go straight across the Atlantic Ocean, you would be in Greenland, which are glaciers, which are always frozen. It's always icy. You can't grow stuff here. It's because this part of the world is heated up by this North Atlantic current. It makes it just warm enough to affect that climate, all right? Also, if you've ever been to like Britain or Scotland or Ireland or anything like that, Britain and Scotland and Ireland in the summertime, like it's warm, like mid 70s. Like if it gets above 80, they start freaking out. They're like, oh my gosh, God save the Queen, or whatever. I don't know. But yeah, like not crazy hot like we have here in the summer, but like warm, comfortable, definitely. And in the winter, like it gets cold, it snows, but it's not like blizzard. It's not like Minnesota cold. But if you look at where Scotland is, here's Scotland, everybody. Scotland is on the same latitude as northern Canada. Like they're really high up there. The reason their winters are so mild is because they're again getting this nice warm water from the Gulf Stream. All right, and you can see how currents affect temperature throughout here. I like how this map has all these pretty arrows showing you where the maps are. You can see the pretty Coriolis effect. Here is Brazil. The Brazil current heats up the eastern coast of South America, so it's really warm. Like it's always pretty warm in this place. Brazil, thank you. Wow, Miss Summers, it's okay. You're gonna get it. It's because warm water's coming down from the equator. The equator's right about here. It's coming down from the equator towards the poles. And over here, if you were to go directly across to Africa, like along the Kalahari Desert, around like Namibia, South Africa, those places, all right, the water's a lot cooler, all right, because the Benguela current is carrying this Arctic water upwards, all right, gets a lot colder. This is why like great white sharks like to hang out right around here. This is the one area of the world, this is a side tangent. Around here off the coast of South Africa is the only place in the world where great white sharks hunt by jumping out of the water and like torpedoing their prey. It's pretty cool. All right. But you can see the Gulf Stream. There's the Gulf Stream. There's the nice warm water. All right. If you think about like Europe's actually pretty far north. Like Rome is right about there. That's like the same latitude as New York City. But Rome doesn't get that cold in the winter. Because it's affected by the Gulf Stream. Cool beans. All right, let's talk about our next current, the subsurface currents or density currents. So this is why I talked about temperature and salinity earlier. Subsurface currents move vertically. So they start here, they start at the top, and end up at the bottom. Or they start at the bottom, now we at the top. All right, it's because of density differences. All right, water becomes either colder or warmer, or saltier or less salty. and that affects the density. All right, around Antarctica, this is a really vital part of the world's climate, if you will. All right, when we talk about climate and climate change, a lot of people will cite Antarctica, things happening around Antarctica, things happening in the ice shelf around Antarctica. And you might be like, well, nobody lives there. Like, low-key, nobody lives there. It's the only place where coronavirus isn't at right now. So why do I care about Antarctica? Because nobody lives there. Well, it's because around Antarctica, you have very dense water, and that kickstarts this whole global conveyor belt. Okay, so it goes wee, and then it comes back up, and it goes wee, and then it comes to the Gulf Stream, and then it goes wee. All right, if the density of the water around Antarctica changes, and this deep current around Antarctica changes, it messes up everything else. It messes up our climate, Europe's climate, South America's climate, Australia's climate, all that good stuff. All right, let's talk about upwelling as it relates to surface currents. Upwelling is kind of the opposite of a density current. Upwelling is when cold water rises from the deep. And you might be saying, well, how does cold water rise? How does cold water rise? Because remember, cold water is really dense. It doesn't want to rise. It wants to sink. Well, it has to do with surface currents and surface winds. All right? Wind will push warm water out of the way, creating a space where cold water can fill in. All right? So the wind affects current. That's the atmosphere affecting the hydrosphere. Haha, looky there. Also, if you have islands, if you have areas of land, like an island in the middle of an ocean, as that cold water current underneath hits that continental crust, the water is forced upwards. So upwelling happens around islands usually as well. This is a positive thing. You want upwelling to happen because cold water has a lot of nutrients in it. It has a lot of oxygen in it. It has a lot of stuff in it that organisms need to survive. That little plankton. Planktons are like the plants in the ocean. They're the base of the food chain. They need upwelling to happen. And all the other fishies need upwelling to happen because they eat the plankton, or they eat something that eats the plankton. All right? So here's a fine example of upwelling happening around this little island. All right. Around these little islands, you're going to have lots of different animals and living things because all these nutrients are abundant here. So, to recap, why we care about currents. They play a major role in climate patterns because they move heat away from the equator and they move cold water towards it, so like a circle. Currents help bring up nutrients from the bottom of the oceans, like upwelling. And currents carry other stuff, all right? If we are irresponsible with our waste, it could end up in a current, all right, especially if you live in a coastal area. Those currents can carry that stuff not just in the area that you're at, but it can carry it all over the world through these interconnected currents, okay? So, that is it for this video. There's another video for how to do the assignment. Please watch that before doing the assignment. All right. And if you have any questions, you know how to get in contact with me.